All right, so Unit 6, the idea is we're going to use the stuff we learned in Unit 5 and before to help us make design decisions about systems. So one kind of stepping stone between Unit 5 and Unit 6 was this concept of non-gain parameter root locus. So in the example system that I have here, the question that we'd like to answer is, where do the closed loop poles go if I vary the parameter z? And so what I want to call your attention to here is that the closed loop transfer function over here, y over r, has this thing added to 1 in its denominator. However, this thing is missing the parameter that we are trying to vary out there. And that was the form of all of our root locus rules from Unit 5. It was always 1 plus k times g times h, where k was the thing to be varied. Now, I don't care if you call it k, you could call it z, you could call it whatever, not s, but we don't have any of those letters out here in front. In fact, the z, the thing that is being varied, is buried inside of this expression in s. And so it's still a valid question to ask, and I think it's still an interesting one to answer. And what we're going to do is, instead of learning a new mathematical technique, we're just going to modify, we're going to mold this problem so that it fits our old tool, the root locus tool. So the idea is, take your closed loop characteristic polynomial, which is this thing, and write it so that it looks like that it equals -1. So here we're going to start with, if the closed loop characteristic polynomial equals 0, then that means that S is a closed loop pole, right? Any S that satisfies this expression is a closed loop pole. And this statement holds for all of these lines, because I'm not doing anything to break this equality. And so what I'm doing here is I'm just massaging this expression until I can get it in the form of the parameter to be varied times a function of s equals -1. And so
Can't you just like subtract 1 from both sides and then have that work?
So if I subtract 1 from both sides, I don't get z times a box. I get
Oh, I
another
see, I see.
polynomial in s and z. And so, yeah, the key is that we need the parameter to be varied out front, multiplying a function and it having it equal to -1. So this is why this boxed thing looks like, maybe I should say, acts like the open loop transfer function from Unit 5. Okay, which means that when these, the poles of this transfer function are where the closed loop poles are when z is small, and the zeros, if it had any, would be where the closed loop poles go when z is large. And everything else we've learned about root locus we can get by treating this boxed function like the open loop transfer function. Okay, and so that's how I got the figure on the right. We have open loop poles at 0 and -2. And that means that the real axis in between them is in, and then they break away at the midpoint and travel north and south. So these are the closed loop pole locations as z varies positively. And I want to point out that these are not the true open loop poles, right? Because the true open loop poles are at -1 and at 0. And here we have an open loop pole, or a quote unquote open loop pole at 0 and -2. So it's important to see that I am treating this red box as the open loop transfer function, but it's not actually the open loop transfer function. The actual open loop transfer function doesn't actually help us here because it doesn't have the parameter to be varied out in front. Questions on this?
So I just wanted to confirm that k was our variable that we were using in the prior sections to vary to see the stability and whatnot and how the root locus looks like. But z in this case is not really k, but one that acts like K.
Yeah, that's the best I can describe it.
Okay.
Yeah. All right. So I think a lot of times, especially when you start to learn about the MATLAB tools available to you and CISO tool and all that, there is a little bit of indignation about why we spend 5 lectures on teaching you how to draw a root locus diagram when it's a couple keystrokes can get you the same result. And my answer to that is that the point is not to draw a pretty picture by hand. The point is to teach you intuition about where open loop pole placement and open loop zero placement can affect closed loop pole placement. And I think that learning the root locus rules actually kind of does an end around and sneakily teaches you about that. So, and we're going to practice that in this unit. But again, let's review what it means to design a system. I think a lot of people, based on the Piazza questions, are having trouble with modeling the system. I haven't actually seen a lot of questions about how to design the control system. So I just want to remind you that the idea is you're designing a system to accomplish some tasks, some objectives. And the very first step of the design methodology that we taught in first week is to establish what those requirements are. And so here, when we're going to be analyzing these systems to design, we're going to ask ourselves, what are the objectives that we're trying to meet? And then the actual root locus diagram tells you where the closed loop holes can go. But I think that just as often, it's important that you know where they can't go. For example, if your objectives require you to put closed loop holes to the left of some vertical line, then the important information to glean from a root locus diagram is, do the root locus branches ever cross that line? Do they ever enter into the region that you need? And if the answer is no, then you need to modify the root locus diagram, or you need to modify your topology so that you can get your closed loop holes into that region. Okay, so what we're trying to do in this unit is to get you to see how different choices of open loop transfer function can affect closed loop root locus. So we're not going to be talking too much about varying topology. That is, most of the controllers and the systems that I'm going to be teaching you about have pretty much a single feedback loop. You can also talk about multiple feedback loops. You can talk about feed-forward design. And these are all variations on the theme that changing a subsystem can have large effects on the system as a whole. But if you're focused on a single feedback loop with the controller acting on the error in the signal right after the summing junction, then choosing what kind of controller to use really comes down to, at the first glance, how many poles do you want, how many zeros do you want, and what should the gain be? And then where should those poles and zeros go? But this is kind of like, we're taking the task of picking a system, and I'm trying to boil it down. If you're restricted to LTI systems, which I think is a good restriction at this point, then the system that you choose for your controller is going to be some poles and some zeros. How many poles? How many zeros? That's up to you. And then possibly a gain. How big of the gain? That's also up to you. So what I'm trying to communicate here is that your very first choice of controller actually comes down to how many poles do you want? How many zeros do you want? So some of the choices, some of the options here have their own names. So for example, if I have 0 zeros, 1 pole, 0 zeros and 0 poles, then what's left? Just K. So this is what's known as a proportional controller. All right, so this block would simply look like that. And that's fine. That just means that your system is going to act proportionally to the error. If the error is big, the actuator does something big. If the error is small, the actuator does something small. If the error is 0, the actuator does nothing, because your system has 0 errors, so there's nothing to correct for. What else could we see? We could see no zeros and one pole. Then it becomes a question of where the pole is. So this would be k over s plus p. Possibly with p being 0. So if p equals 0, then we've got an integrator. This is called an integrating control. If p is non-zero, then I think this doesn't really have a true, like a kind of control-y type name. But what it is, it's a first-order low-pass filter. So let's flip that around. If you had 1, 0, and 1 pole, then your block would look something like k times s plus z over s plus p. And then you have, of course, now 3 degrees of freedom. Where does the k go? Where does the z go? Where does the p go? But again, if p is 0, then what are we looking at here? We're looking at k times s plus z over s, which if you break it up, looks like k times 1 plus k times z over s. And so I'm drawing this out because I want to make it plainly clear that this controller looks a little bit like a proportional controller, and it looks a little bit like an integrating controller, which is why it gets the really fancy name, a PI controller. Right? This is a controller that acts proportional to the error, but also proportional to the integral of the error. Okay. If P is non-zero, then I think this fails to have a fancy name. This is just, yeah, this would just be maybe a notch filter or something like that. No, it might be a lead or a lag compensator. That's also true. So what else could we do here? We could keep incrementing up these numbers. So if we have well, so we've done P and we've done PI. I guess we should start talking about PID. So if you have 2 zeros and 1 pole, and that pole is at the origin, then your controller transfer function could look like a constant times a couple of zeros. Could be complex conjugate, could be distinct, could be repeated. Don't quite know yet, over S. And so if you distribute or if you FOIL out the numerator here, this equals k times s squared plus z1 plus z2 s plus z1 times z2 all over s. And so what I'd like you to see is that this equals k times s plus z1 plus z2 plus z1 times z2 over s. And so the big picture here is that we have a derivative, a proportional, and an integral term. Okay, so this controller will tell the actuator what to do based on the sum, the weighted sum of the derivative of the error, what the error currently is, and what the integral of the error is. And we'll talk a lot more about PID controllers at the end of today or on Wednesday. But the key here is that these S's are telling us the dynamics. The fact that there's no S there means it's a proportional controller. The fact that there's a multiply by S there makes it a derivative. And the divide by S over here is an integrating controller. Okay. And then you can pick different weights for these different terms based on what K, I guess K multiplies all these, sorry. But you still have 3 degrees of freedom here. You can pick Z1, Z2, and K such that you can pick any weight on all of 3 of these terms. Okay, so with that in mind, I'd actually like to go back to this system, which was the final root locus example problem from last unit. And I want to analyze this choice of controller. which you can now call an integrating controller. With this choice of controller, the root locus is as we've drawn here. And let's talk about what some objectives for this system might be. Just spitballing here. What, in terms of stability, in terms of steady state performance, in terms of transient performance, what are some ideas that you have? Like just make them up about what this system should, what the specs for this system should be.
Overshoot less than 10%.
Okay.
Steady state.
Hold on. That's a transient requirement, not a steady state requirement. I mean, that's fine. That's what I was asking for. But when you close that sentence with steady state, it confused me.
Okay, my bad. How would I say it differently?
I think you meant that in response to a step, there's no more than 10% overshoot.
Oh, okay, got it.
Is that what you meant?
Yeah.
Okay,
Yeah.
sweet. Anything else? Any other suggestions?
In response to a step, it has to have a steady state value of 5 whatever unit.
Okay, so if a unit steps comes in, we want something with 5 of those units out?
Yep.
Okay, so that means, I think one way to interpret that is that we want a DC gain of 5. Right, because in steady state, a step input looks like a DC input. And so I think what we'd like is in DC or in steady state conditions, 1 volt in gets us 5 volts out, or whatever units, as you say. Okay. So part and parcel of both of these are that the system be stable. Right? If I've got a step input and the system blows up, I've ruined my 10% overshoot. Also, I have a gain of more than 5. So I think both of these, either of these, imply the need for the system to be stable. Yeah, okay, let's work with that. So if these are our list of requirements, does the proposed controller, this integrating controller, work for us?
Not too sure about the DC gain part. I think it's a little hard to see, but I feel like there's a point on this root locus where we can get an overshoot of less than 10%.
I agree with that. If the system were second order, then a 10% overshoot would correspond to something like poles on this cone.
Mm-hmm.
Cool. So then we've got these spots that open up. If the system were second order, looks like it's going to be fourth order. But maybe we can make an argument that if we put the slow poles here, then the fast poles can be neglected. I think that we might be able to make that kind of argument. The problem I see, and I think it is with the DC gain, is that if we want, another way to phrase that is that we actually want error to a step. Now, that's a little strange here, but that's because the student suggestion was a little strange. Thanks, Joseph. The idea is, I mean, I opened it up, right? If there were no error, then a unit step in would produce a unit thing out. And we explicitly now don't want that. So I think by specifying the DC gain of being not 1, we have said that in response to a step, we need error. Like that is part of our system design. Now, tell me, if a step is input to this system currently, what type of system is it? And how much error do you expect? Type, like type number. way back. Remember, like 2 weeks ago, 3 weeks ago.
One, because there's one integrator.
Exactly. This is a type 1 system because there is this integrator in the forward path of a unity feedback system. So because this tells us that this is type 1 tells us that error in steady state due to a step reference is 0, which I've been saying is a good thing, but in this particular case, because of the suggestion, it's actually a bad thing. So is this the right controller for our requirements? No, we didn't have to put an integrator in here in this controller. In fact, this integrator is actually what's giving us the headache here. So get rid of it. So what if we just did proportional control? Would that work? These are the kinds of questions that I'd like you to start asking, especially about the term project, but in general as control engineers. If this controller doesn't work, what are my other options? The other options are maybe go through this list. Maybe go through and say, if I don't want to poll at the origin, do I want to poll elsewhere? Do I even need any polls? Let's start at the beginning. Let's say my guess number 1 is just proportional control. Then I've got the 3 plant polls and no additional dynamics. So I'm going to have 3 asymptotes. The only part of the real axis that is in the root locus is going to be to the left of these 3. The center of mass is actually going to be, because they're all lined up, the center of mass is going to be right here. And because I have 3 poles and no zeros, I'm going to have 60-degree asymptotes. So I think this is enough for me to, conclude that this would actually be a legit, maybe a legit design. I think we'd have to check the cone angle. So let's see. Anyone off the top of their head know what the beta angle should be for an overshoot of 10% in a second order system? I would be super surprised if anyone did. Okay, so let me fire up my calculator here. Wait for it. Okay, so we want to find the beta corresponding to a 0.1% overshoot. So the zeta formula, this looks like the square root of log of the overshoot, overshoot squared divided by pi squared plus log of the overshoot squared. Zeta of 0.59, so I want the inverse cosine of zeta, 53-degree cone. Okay.
So is an integrator for when you want the output to match the input, basically?
Well, so I mean, yeah, the presence of more integrators here in the controller is going to necessarily, at least as long as you have unity feedback, the presence of more integrators here is going to increase your type number. Increasing your type number will increase the number increase the range of reference signals that you can track perfectly in steady state. Did you understand that summary?
Mm-hmm. And so even if there's a disturbance later on, it'll still help it drive to a certain value?
So we haven't really, type numbers don't tell you exactly what happens in response to a disturbance. Actually, that's an interesting question, but it's not one that I'm ready to answer right now. But certainly, more integrators will help you track more reference signals. And I think it's probably true that more integrators will help you reject disturbances more quickly, but I'm not prepared to swear to that. Maybe I can type up a Piazza post on that in a moment. let's see here. We've got a 53-degree cone. So these were at J and -2. So 53 degrees looks like this. There's our 10% overshoot cone if the system were second order. I have to keep adding that off caveat. And so the angle of departure here, I don't know, should we figure that out? It should probably be pretty easy. So theta departure is going to be 180 minus 90 minus 90. Job done. Because there are no zeros. So the angle of departure here will be 0. So it goes flat, and then it goes out like that. Perfect. Okay, so just by sketching this root locus, we see that there are going to be points in which the slower closed loop poles are going to have overshoot of 10%. If I reduce the gain, then I'll be inside the cone. So this point should give me a upper bound on my open loop gain K in order to satisfy the 10% overshoot requirement. That might be something you have to check after the fact with this requirement, because the K will also tell you or help you dictate your DC gain. Is it reasonable to expect that these two closed loop poles will dominate? Is that even a sensible question to ask? What do you think?
No.
They'll dominate more the further to the right it goes, but the system is wanting it to be further to the left.
So nothing about our requirements actually require us to go further to the left. I think that
Within the cone, though, I meant.
oh yeah, so sorry, within the cone, that there is this tension that to get these two poles to dominate, we would have to increase the gain, which might send them outside the design cone. But look at what they're trying to dominate against. They're trying to dominate an overdamped mode, which would have the tendency to do what? Bring the overshoot down because it's overdamped, because it is sluggish in terms of oscillations. And so I don't really think that we would need to dominate this one very much. I think this pole is actually kind of helping us to achieve this under 10% overshoot. So I think the real devil would be in the details about here, how big can we make K to get this DC gain of 5? And to do that, that actually is something that you can't directly do from the root locus diagram. To do that, we'd have to go and get the closed loop transfer function. So this would be K, if we're just using proportional control, over S plus 2, S squared plus 4S plus 5 plus K. And if I want to evaluate this at DC, so at DC, that's S equals 0. The gain here at DC is going to be K on 2 times 5 plus K. So we get K on 10 plus K. Set that equal to 5 and cross your fingers, I guess. So K is 50 plus 5K. Oh no, this does not look good. So we get negative 4K is 50. This looks disturbingly familiar. So we get a negative number here for K. That's the only way to get a DC gain of 5, which is bad news. Why? Because our root locus diagram assumes K is positive. So this is, it's not the end of the road, but it just means that the analysis that we did is invalid for the K that we would need to get a DC gain of 5. Oh man, it's a bummer. So what could the fix be?
Could you add another something that would be like a gain?
Yeah, I think that that's a good idea. So this lightning bolt is just my little symbol. It means contradiction in math. But in this particular context, it means that the analysis that we did led to a dead end. So I think that we have to make a new guess. Let's see if I can go a little faster here. Okay, so guess number 2. If the lesson that we just learned from that iteration is we need more stuff, more gain on top, right? If we had a multiplier up here, then that actually would help the situation. So I think our second guess should be add an open loop 0. So I propose the new controller block should be something like k times s plus a z. And here we're running into about the bounds of our usefulness of root locus, because remember, root locus is really about how did the closed loop poles move as one parameter changes. And right now, we have 2 parameters to change. So, but we can at least do our best. We can maybe set a couple values for z and draw several root locus diagrams, one for each of those values. So we'll start again with the plant poles. And so based on our analysis, I think the bigger z is, the easier this will be satisfied. Although the bigger z is, the bigger both of those become. So we might actually be out of luck here. I don't think this, well, I mean, we can at least do this analysis now. So at DC, well, how would this change? This would be now s plus z and s plus z. Yeah, so I think that overall we're going to get the kz canceling with the kz. But we can give it a go at least. So this is kz, 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 and it's the same story. So now, although maybe we can have the z be negative. Oh, now we're living dangerously. Is it okay to have a negative z? A negative z would mean you'd have an open loop 0 over here. Is everyone comfortable with that? So why do I propose having a right half plane 0? Well, because I know the product of k and z should be this negative number. And I know that k shouldn't be negative because, well, I guess we could have k negative, but the setup here is for a root locus with positive k. So I guess to live within the constraints of what I've taught you, we're going to keep k positive, which means we should consider z being negative. Z being negative is fine. It just means that the 0 will be in the right half plane. So the root locus now for positive k is going to be this region. And then that's it, right? Because now there are 0, then there's 1, then there's 4. So this is the only region of the real axis that is in the locus.
So you just have to make sure that you choose a k value that keeps it away from that 0.
Bingo, bingo. We have a constraint on, well, I guess, strictly speaking, that constraint is at the origin. But yeah, so just the fact that there is a root locus branch that goes in the right half plane does not necessarily mean that the closed loop poles will be in the right half plane, right? Because we can pick a k, at least nominally, we can pick a k that puts us in here. So riddle me this, how many asymptotes will there be now? How many open loop poles are there?
2 asymptotes.
3.
3 open loop poles and 1 open loop 0, which means that there will be 2 asymptotes. Okay, so you're always looking for the difference of m and n. So therefore, it's going to be 2 asymptotes. That means that they're going to take off at 90 degrees plus and minus. And the further to the right I put this 0, what effect will that have on the center of mass? Can you predict that? This is an interesting question.
Would it push it more to the left?
That's right. Yeah. So the further to the right the open loop 0 is pushed, the further to the left the center of mass is pushed. because a 0 acts like it has negative mass. Okay, the way I think about it is if this were a pole, then it would drag the center of mass to the right because you're moving some mass to the right, which means the center of mass has to be dragged to the right. But then just flip that reasoning around. Because this is a 0, it's going to have the opposite effect of the center of mass. So that means the center of mass is probably going to be somewhere out here, which means we've got asymptotes out here, which is actually a good thing for our stability. Okay, it means that the only chance this system will have to go unstable is from this closed loop pole. So I think that's this is a promising design. Are there any questions on that? Okay, so we went through a list, a short list anyway. We started simple with the proportional control. Well, we started with what was given to us, which was integral control. And then we kind of cooked up some make-believe requirements and found out that the thing that was given to us wouldn't meet those requirements. So we said, let's try something else. And my recommendation is to start simple. And because simpler is better in some respects, it's fewer things for you to design. And as long as you can meet the requirements, then why overcomplicate things? However, a proportional controller didn't meet the design requirements, so we had to step it up. What we stepped it up to was actually informed by how the system failed to meet the requirements originally, and that was the gain was too low, so introducing an open loop 0 was my idea to boost the gain. It didn't have that direct effect because remember, if you introduce an open loop 0, it appears both in the top and the bottom of the closed loop transfer function. But indirectly, the effect it had was it allowed us to draw the root locus for positive k by choosing a negative open loop 0. Sorry, z being negative, which means the open loop 0 is technically a positive number. All right. So this one, I'm taking the audience participation variable out of it, and I'm cooking up these requirements for us. So I'm going to run through the same kind of thought process here, but I've got a simpler plant transfer function. So the plant has an integrator. The plant has a pole at -4, and let's see if we can run through the list. If the requirements are for a type 0 system, then I think that's actually not what I meant. So there's a correction here. So listen up, people. I want this to be a type 1 system. Even when I don't ask for student participation, I still manage to screw it up. So if I want this to be a type 1 system and the plant itself already has an integrator, that tells me that I don't need an integrator, so no integrators in the controller. Because if I were to add integrators in the controller, I would get, type 2, type 3. I would increase the type number correspondingly. So that tells me that my controller transfer function shouldn't have any integrators. It can have other poles, but just no integrators. If I want the system to be stable, then I think if I were to just do proportional control, that would be pretty good, right? In terms of proportional. So if I had proportional control here, then we would get that, and then we would get that. These are supposed to be vertical. These are always stable. You could, throw a dart on a number line, and you would get a gain that would give you a stable system. And it would be type 1 because of the plant integrator. My next question is, does it satisfy this settling time requirement, which is admittedly quite vague. One way to interpret this might be, could the settling time be faster? If the answer is no, then we've got as fast as we can do. If the answer is yes, then maybe we didn't quite optimize our controller enough. So Where should I put the closed loop poles to make the settling time fast?
Closer to the right?
Try again.
Closer to the left?
Further to the left, yeah. So remember the settling time for second order systems anyway was take the negative of the natural log of your settling time threshold and divide it by the product zeta omega n. And this represents the real part of the poles. So if the real part gets larger, or the absolute value anyway, of the real part of the poles. If the real part gets larger, the settling time gets smaller, regardless of what delta is. And so one could draw the line of constant settling time. This is constant T delta. And the further to the left this line is, the faster that T delta is, or the smaller the number T delta becomes. And so once we break into the complex conjugate poles, the actual settling time of this system is fixed. It does not change whether the gain changes. And if you say, well, what if we didn't have complex conjugate poles? Well, then you're guaranteed to have a very slow overdamped pole. So I think that this system meets the first two, but not the last requirement. So I think we should start over. So now the question becomes, and I actually would like to open this up to the class. What should our next guess be? Our first guess was proportional, and that doesn't meet the third requirement. So what's next in line?
Could we, is it too much to add another open loop or a closed loop pole?
We can. So maybe the next guess would be K over S plus a pole.
Sure.
I think that really you have two choices. You could either do this, or the next most complicated thing would be that, or some combination thereof, right? But that would be, if we know the proportional control doesn't work, then maybe proportional and a pole or zero. I think that those are the two candidates. Mm-hmm. So if we go with this one, we have, well, what are our choices for P? What do you think here? If it's a single pole, then P has to be real. So all of a sudden, we get this entire complex plane narrowed down to picking a place on the real axis for the pole. So I think then we have now three choices. It could go here, it could go here, or it could go here. All right, so I'm taking this infinite possibilities. A pole could be anywhere in the complex plane, but since we're only adding one, the pole can only be real, which is still technically an infinite number of possibilities. But I'm also carving up this infinite number of possibilities into three cases. It could either be here, here, or here. To the left of the plant poles, in the middle of the plant poles, or to the right of them. Now you tell me, which one of these is clearly a bad idea?
The right one.
Yeah, this is clearly a poor choice. If you had left that there, then you would get an unstable system for all gains. So that's bad news. I'm glad that that's been eliminated. What happens if we leave it as the middle one?
The faster poles, the ones on the left-hand side.
Yeah, you get that guy going that way. You get these two coming together, and then they'd have to break off into the right half plane. I think that we are still failing our settling time requirement. So I think that this choice for pole is also poor.
What if you added a zero so that it wouldn't cross over to the right?
Yeah, I think you're starting to see the idea is that adding a pole isn't helping our problem. In fact, it's making it worse. This pole actually has the same problem as the other case that I just considered, but except that the range in here is a little bit wider, but it still goes into the right half plane and it still doesn't really improve the settling time at all. So I think that we have decided that an extra pole, regardless of where it's placed, is not going to help us. So let's talk about where the 0 should go. Again, the 0, if we're adding a single 0, it should be real. That means we have 3 choices. Tell me, why is this choice a poor choice?
Moves center mass to the left, which causes the breakout pulls to cross the imaginary axis faster.
So actually, if I take away the other choices, I hope that you'll see that this becomes part of the root locus. So there's actually no gains that would stabilize this system, because we've now drawn a closed loop pole into the right half plane for all gains. So let's consider this option. Now what does the root locus look like? It looks like this, and then that. So congratulations, we have stabilized it. We have ensured that it's type 1, but we have not improved its settling time, because guess what? We've got a super slow overdamped mode here. So by process of elimination, hopefully this last one will work, because we're running out of time. So if I put the 0 way out to the left, the root locus now lies between these two, but then again to the left out here, right? If you do your even and odd checks, so we've got a pair of closed loop poles that head towards each other. Well, how are they going to get from here to over here? Because this is where they have to end up. They have to break away. Their breakaway will be somewhere in here. I'm not quite sure where, but you could do the math to do it. And then how do they get over here? They've got to break in. And so what you'll see is that we'll get this kind of behavior. Now, does this meet our requirements? Yes, it's type 1. Yes, it's stable. And we can put this 0 as far to the left as we want. Like technically, we had no manufacturability requirements. And that means that if I place a line of constant settling time out here, then I'm always guaranteed to be able to cross it arbitrarily far to the left. So I think that we have winner, winner, chicken dinner. This is what we want, where the 0 should be large. Okay, so I hope that you see the power of this technique is that I didn't have to iterate through a whole bunch of numeric Z options. I took the choices of where I could put the Z and I narrowed it down into 3 cases, and I went through a process of elimination on those cases. The way that I eliminated them was by knowing how to sketch root locus diagrams. Maybe not precisely and accurately, but at least in the gross rules that we've learned, how many of these were we able to immediately throw away because they would produce unstable systems? Most of them, actually. Many of the systems that we considered, we get to throw away quickly because they're unstable. And I would argue perhaps even more quickly than if we used a computer for this. But that's definitely up for debate. Okay, I've got to close there. We will pick up more on how valuable open loop zeros are next time. Thanks, everyone.